All right, so we're quickly going to recap a couple of the problems we started last time and then move on. So this is section 4.2, and the first question asks you really kind of in a somewhat related way about the complementation rule, but it's stated like this. They want you to figure out which one of these sentences pertains to the probability of B or not B when the event of B represents randomly selecting somebody with type B blood. So if B is the event of selecting somebody with type B blood, what's B bar or not B represent?
Not B blood?
Yeah, just not B blood. Now that probability is 1, so that deletes this one. It can't be impossible because that would have a probability of 0 associated with it. The first choice says the randomly selected adult does not have type B blood. Well, that person could, so that one can't be right. The second one says the randomly selected adult has type B blood. Well, could also have something other than type B blood, so that one's not right. Finally, this one looks like it works pretty good. If it is certain, meaning probability of 1, that the selected adult has type B blood or does not have type B blood, which sounds kind of silly, but that's what it's saying here. Basically, it's saying that one of those two things will happen. Now, let's move down to the next one here, which gave us a chance to work with some probability rules. And maybe to kind of start this, I'll write down some notation and also write down some, well, more notation, I guess, for an event. But let me start out with this. I'm going to look at some probabilities. And this is what's called a Venn diagram. You don't have to draw this.
We can't see it on
Yeah, I'm catching up there. I just want you to have a good conceptual understanding for what's happening. So here's event A, here's event B. If I wanted to calculate the probability of A or B, well, one way to do that is kind of directly. You can say, oh, well, it's a probability of A plus a probability of B. But that's a little bit of a problem because when you do the probability of A, you get everything here. And you do the probability of B, you get everything here. Can anyone see where maybe I've overcounted things?
We can't see it on the screen.
Always, oh, I'm sorry. I thought you were, never mind, my bad. All right, so my Zoomers are gonna have to wait for me to get this, the overhead lined up. When you said that, I'm thinking, oh, I didn't hit the button here. But no, it's the button over there. Too much technology going on here. Did you ever hear of Murphy's Law?
Yeah.
What's Murphy's Law say?
Anything that could go wrong does go wrong.
Yeah, yeah. If there's a chance that something can go wrong, it will. So that's what's happening with me. What's the probability associated with Murphy's Law? If it can go wrong, it will. So what's the probability associated with that?
1.
1, yeah. Probabilities are between 0 and 1. Okay, I think I've stalled long enough. There we go. Now you guys can see, right? So if this here, this box represents my sample space of everything that can happen, and this is event A and this is event B, probability of A or B is a probability of A, so everything in this circle, plus a probability of B, everything in this circle. But there's a problem with that. Can anyone see why we've overcounted? Or where we've overcounted? Yeah, in the middle. And that middle piece is where A and B overlap. So in order to calculate this probability, you would have to subtract the probability of A and B. So, okay, that's fine. Now there's a different kind of thing that can happen here. And it gives me a chance to remind you of something that I mentioned the other day. Again, this is a sample space. So let's draw a couple events, A and B, but this time they're a little bit different. So what's different about these events? They don't overlap. So if I wanted the probability of A or B, this is going to be a probability of A, probability of A plus a probability of B. Well, what's happening is that A and B can't overlap. There's no intersection, so that's it. That's all you're going to have to do for your calculation. When you have events like this, A and B are mutually exclusive. They're mutually exclusive events. If one happens, the other one can't. If you have type A blood, you can't have type B blood. If you go to restaurant A, you can't go to restaurant B. So one of these things happens, then the other one can't. So it's really meaning that this intersection is zero. They can't both happen. Now there's another name for mutually exclusive, and in the book uses this one. It's disjoint. I like mutually exclusive because it's a little bit more descriptive of what's going on here. Basically saying if one happens, the other one's excluded from happen. They can't both happen. One excludes the other. So that's what's going on here. They can't both happen. Let's bring that back to our current example. Let's see. We selected C up here. And let's come down to example B. For example B, I'm also going to introduce some more notation here. And that is for an accurate order. Now because we have a restaurant A, as opposed to what the actual printed version of the book would have, would be like McDonald's or Taco Bell or something like that. What I'm going to do, because I can't use A for accurate, I'm going to use R for right. It's got the right order. Or R is going to be the event that the order is correct or right. You got your order right. So I'm just going to leave that as some notation that we're going to use in the second part of this event, or second part of this problem. But for starters, let's see. For starters, we want to figure out what's the probability of getting an order from restaurant A or restaurant B. Okay. Now, in general, when you're calculating these probabilities, you have to calculate it like this. Probability of A or B is a probability of A plus a probability of B minus the probability of the intersection. But you can't eat at restaurant A and B at the same time. So these are disjoint or mutually exclusive. So really to calculate the probability of A or B, you're just going to calculate the probability of A plus the probability of B. You don't have to worry about the intersection because they're mutually exclusive. Now the question is, what's the probability of eating at restaurant A? Well, I've given you the marginal totals here. There's 362 people who chose to do so out of 1,118 in the survey. Probability of B, that's going to be 325. I got that right? Yeah, 325 over 1,118 for a total of 687 out of 1,118. That's the probability that somebody randomly selected from this table eats at restaurant A or B. So kind of a nice friendly one, and it's friendly because A and B are mutually exclusive. We okay on that first one? Yes.
1,134.
Oh, I'm sorry, did I grab the wrong number? Where are you getting 1,134?
On the total, on the,
Oh, I'm sorry, I'm looking down here, not up here. Yeah, 1,134, all right, my bad. Thank you. 1,134, yeah, 134. So I gotta make these 34s. Thank you. All right, so Murphy's Law strikes again. 34, 34, 34. Let's move down to the next one, where I'm a little more anxious to look at things. And on the next one, we want the probability of getting a restaurant from, or order from restaurant A. Come on, what's going on? Order from restaurant A, or getting an accurate order. Now for us, I use the notation for as R, just because I wanted a letter that I wasn't already using. So the probability we're trying to calculate is the probability of A or R. So probability of A or R. Now there's a difference between the two probabilities we're just working with. These up here were mutually exclusive events. Can you get an intersection between A and R? Can you eat at restaurant A and get an accurate order?
No.
So then they're not mutually exclusive. So you're gonna have to calculate this kind of the long way. Probability of A or B is the probability of A plus probability of B minus the probability of their intersection. How does that translate to this example? Well, it's just going to be P of A plus probability of R minus probability of A and R. That's going to be the probability we're going to have to fill in. Okay, here's what I want to use the 1,118 as my denominator, not the previous one. So let's do that. And in general, what I've given you are the marginal totals. So those are marginal totals, and in yellow there in the corner is our overall total. Let's see, up here, this A. Oh, you know what? We're still working with this one. So my denominator is still going to be 1,134. What's the probability of eating at restaurant A? Well, I think we already got that one. Yeah, thank you. 362 over 1134. How about the probability that your order was accurate? Now, I guess I highlighted the wrong marginal totals just a second ago, so let me put these in play. What's the probability that your order was accurate? How many accurate orders were there altogether?
989.
Be 989, right? 989 or, yeah, thank you. So 989 over 1134. Minus the probability of intersection. Now let's think about it in words first. What does A and R mean in terms of words? Well, you ate at restaurant A, and what else happened?
Not an accurate order.
You got an accurate order. Yes. So, how many of those people were there in this survey? How many people ate at restaurant A and got an accurate order? 330. Good. So 330 over 1134. And so now it's a matter of just adding these all up. So let's do that. Unless somebody's already beat me to it. 1,021 over 1134. And that's your final answer. what we're doing by subtracting off that piece is subtracting off the double counting. Because when you count all the accurate orders and you count all the people who ate at restaurant A, you're double counting that total there of 330. So 1,021.
Could you pull it to the side?
Okay. So that's stuff that we did the other day. Let's move on and break some new ground and talk about probability of A and B, or probability of successive events. Both events happening. And so for this second part here, in example C, I'm going to introduce some notation, and that notation is down here. I'm going to let B1 and B2 represent the event of randomly selecting somebody who ate at Burger King on the first draw, and B2 represents the event that somebody ate at Burger King on the second draw. And similarly, you can define C1 and C2, that kind of thing. We're going to look at this probability in two circumstances. One is the probability when we're sampling with replacement, and the other ones we're going to be sampling without replacement. So with replacement means you're going to look at this individual and notice if they ate at Burger King or not, and then put them back into the mix. Which, okay, it feels a little bit weird. It's like, well, why would you want to do that? But that's the way that with replacement works. So let's take a look at with replacement versus without replacement. Now, when we calculate these probabilities, lowest terms is not my priority. Getting that right is my priority. So let's take a look here. Starting out, what's the probability that somebody ate at Burger King? If you just randomly selected somebody, what's the chance that they ate at Burger King?
362 out of 180 or 18.
Close, you read the wrong column. 318. But you have the right idea. 318 over 1,118. That's on the first draw. Now, for whatever reason, you pick that person out, you look at where they ate, and then you throw them back into the pile, mix it all up, and you draw again. What's the probability that on the second draw that you pick somebody that went to Burger King?
Same thing, right?
18.
Same thing, yeah, same thing. 318 over 1,118. Now, the only thing that I would really like to see here or care about is if you maybe write that as 318 over 1,118 squared. I don't care about lowest terms. It's just not a part of this course. So that's the first one. Although it feels a little weird. So why would you want to poll the same person twice? And that's a legitimate complaint. So let's look at this probability another way. We're going to sample, so 318 over 1,118. But this time we're sampling without replacement. So we look at that one, we set it aside. Notice that that's going to change this probability. What happened with the first event here didn't change this probability. But here, when you take that one out and put it aside, it's going to change the probability. What's this new probability going to be? How many people are left that ate at Burger King? 317 over
117.
1,117. Yeah, it's changed the probability. Yeah, so well, on this first draw, so this is the first draw. On the first draw, we said, okay, there's a 318 out of 1,118 chance of picking somebody that ate at Burger King. So you got lucky on the first draw, so you're taking one out of the numerator, because there's one less person in the pool that ate at Burger King. And there's also one less person overall, because you took somebody out of the overall pool. So that's why. Yeah. Here, on the first draw, you looked at it, and then you put it back and shuffled it up. So that's why it didn't change in the second draw. It'd be like, well, the probability first draw and the second draw is going to be the same if you're sampling with replacement. Yeah. All right, cool. So there's going to be a difference that's going to be important about this later on when we work with this, and that is this is going to lead to what's called dependent events. But right now, we don't have to worry about that so much. Are we okay with the front side of this handout? All right, let's move on to the second part, second handout or second page here. Oh, here we go. So this one, I left us to fill in our own table because you're going to get something like this in one of the homework problems, and I just want you to practice what's going on with this table first, so that way you're not blindsided. Question?
There's one last question.
Oh. I'm not going to take time to do that last question. It's just kind of a repeat of this. Yeah, thanks. In exercise 21 through 24, use the results from the one-panel THC test for marijuana use, which is provided by the drug company Drug Test Success. Amongst 143 subjects with positive test results, there are 24 false positive results. So let me kind of highlight that for a moment. We've got 140 subjects with positive test results. There are 24 false positives. So the 143 is one of my marginal totals. It's one of the totals on this outside. Where should I put that 143?
On the very right bottom.
Right down here?
Yeah.
Yeah, because there's 143 results that are positive. Now, of those, there are 24 false positive results. So what's going on with a false positive result? How can you get a false positive result? What's happening when you get a false positive result? Does that mean you use marijuana and you got a positive test? Or does it mean you don't use marijuana and got a positive test? Which one of these is a false positive?
Doesn't use it as a positive test.
Don't use. So that's going to be 24 here. 24 here. Now, if there's 24 here, how many have to be true positives? How many have to be up above there?
19.
119. And you get that by subtraction. 119. Great. So that's that first column. Among 157 negative results, there are 3 false negatives. So, where's that 157 gonna go?
Total negative.
157, those are your negative tests. You've got 3 false negatives.
Uses.
Uses. So they use, but they got a negative test, so that would be a false negative test. What's gonna be here then? 154. We can put in some marginal totals that might help us out later as well. So let me put in some of those. So that'd be 122, this would be 300, and this would have to be 178. Okay, so those are all our marginal totals. And a lot of times it's helpful and almost necessary to have these marginal totals, so That's why I left some space for them. We're gonna repeat the same kind of calculation we did just a moment ago. That is, let N1 and N2 represent the event of randomly selecting somebody who tested negative on the first test or on the first and second draws respectively. So let's start out with that first probability. What's the probability that the first person tested negative?
57 out of 300.
Got a 157 out of 300. Do we agree with that? I heard a little dissent. Well, there's 157 people who tested negative out of 300 people overall. Can anyone tell me something special that I should be noticing as I do this problem? Anything at all? Anything grab your attention? Something, maybe with replacement is the big thing that should catch your eye. Yeah, because the next probability is going to be 157 over 300 again, because you looked at that first result, put them back in the mix, shuffle up the cards, and drew again. So 157 over 300 squared. Done. Do not worry about lowest terms. Why don't you try the next one? The next one has you sampling without replacement. So that's the big thing to notice over here. Samples are taken without replacement. All right, so on the first draw, there's 157 ways to get somebody who tested negative. Good. Well, you're taking one out, right? Because on the first draw, you pick somebody who tested negative. So there was 157, so 156. And now there's only 299 in the pool that are left. And that's fine. Leave your answer just like that. I'll be really, really happy. All right. So it makes a little bit of a difference. And in particular, what I want to notice for you is that here the probability remained the same. Here the probability changed. And because there was a change, that means that these two events are dependent. What happens with the first one changes the probability of the second one. So these are dependent events. Here, what happened with the first one didn't affect the probability of the second one. That probably was the same. So what do you think I would say in contrast to that? Instead of dependent, there are independent events. Good. Independent events. Well, independent events are really just the N1 and the N2. Those are the events. It's not really necessarily the probability, although it is related to the probability. In fact, down below, I've got a little definition for you. Two events, A and B, are independent if the occurrence of one does not affect the probability of the occurrence of the other one. So there's a nice example towards the end of this today where we talk about independent events and flipping a coin. Flipping a coin is going to result in independent events, but I want you to see that calculation. We'll get there in a little bit. The thing that you want to remember for the test this Wednesday is that Sampling without replacement leads to dependent events. Sampling without replacement leads to dependent events. Sampling with replacement is going to give you independent events. Okay, that one looked good. Good there. Let's go back and look at another one using one of these calculations. So this is the probability of A or B as opposed to the probability of A and B.
So you also said that sampling with replacement leads to independent events,
Yes. So
it's vice versa?
sampling without replacements, dependent events. Sampling with replacement leads to independent events. Yeah.
Thank you.
Yep. Thanks for the question. All right, so I'm going to come up with some more notation for these things, just out of convenience for us. So we're going to let the event U be the event that somebody that's randomly selected uses marijuana, and then I'm going to do POS as a event that somebody randomly selected tested positive. So what this is asking me for is the probability of U or the probability of testing positive. Typically speaking, I like to give my events names that kind of reflect what they stand for. Now, according to this little thing on the sample space that I did just a minute ago, probability of A or B is the probability of those two things summed, so probability of A plus probability of B, minus the probability of their intersection. So translating it here is going to be the probability of U plus probability of testing positive minus what? What do I need to subtract there? Well, I could have some double counting here, so I need to subtract off,
U and POS.
yes, of their intersection, probability of U and positive. So somebody that uses and tested positive. Why don't you give yourself a minute, see if you can't figure out these probabilities. Those are going to go all the way back to our table. If you're watching this later, you can pause the video. What's the probability that somebody used? What's the probability that somebody tested positive? What's the probability of those intersections? If you're on Zoom, you can throw in your final answer. Throw it to me privately on the chat. There's a couple cameras I'd like to see turned on, if you don't mind, please. And if you're having issues with your camera, please send me something privately in the chat. Okay, so let's take a look here. What's the probability that somebody uses according to this table? Good. You got to go to the marginal total. There's 122 over 300. Nice. Grace, what's the probability that somebody tested positive?
143 over 300.
143 over 300. Excellent. Gabby, I need to know now, what's the probability that somebody used and tested positive? How many people were there in that group? How many people were users that tested positive?
Users,
Yes.
would it be 265 over 300?
No, you wouldn't have to add up any numbers to get that.
119 over 300.
So of the people who tested positive, only 119 were actual users, so that would be you and positive. So 119 over 300. Awesome. Thank you. For a total of, let's see, there'd be 146, right? Over 300. And that's it. That's it for this one. All right, comments or thoughts on that one? All right. All right, somebody put in 246. I'm guessing you fact fingered the one there. So, okay, let's keep going. Come on. No, wrong one. Still wrong one. There. Okay. We're going to talk about the 5% guideline. Now, when you sample with replacement, what kind of events do you get? Independent. So sampling without replacement gives you dependent events. But let's take a look back at a couple of our independent and dependent event calculations and just notice something. Let's see here. Is there a big, do you think there's a big difference in the probabilities if I calculate a decimal value between this and this? Probably not. Now, there's some guidelines that we're going to give you that say, you know what? Under these guidelines, you can replace this more tedious calculation with this easier calculation. That's our little guideline that's coming up next. It's called the 5% rule. And it turns dependent events into independent events. It turns a tedious calculation into something a little bit more user-friendly. So let's see when that happens, when we can do that. So that's here. You can treat their events, even though they're dependent events, you can treat them as independent if your sample is no more than 5% of the population. At that point, you can treat the events as being, or treat the selections as being independent. Even though they're not, it's okay. We're just going to kind of wink and nod and ignore that because it's just a little bit, it's actually a lot easier to do it if they're independent. Because all you have to do is square it or raise it to some particular power, etc. So let's do a couple questions on that first. Nate?
You said if it's if the sample is less than 5% of the population, right?
Right. Yeah. Now there's another way that you can work that. Let me clean this up a little bit here. All right. Accordingly, there are 15,958,866 adults in a region. Whew. Hope that's a big region. That's more than there in the state of Michigan by about 60%. If a polling organization randomly selects 1,235 adults without replacement, are the selections independent or dependent? What do you think?
Dependent.
Dependent. All right, we're gonna vote for dependent. Do we agree on that or disagree? Agree, all right, thank you, Chloe. They're agreeing with you. Yeah, they're dependent automatically. Now, let's read a couple problems down here. Are the selections independent or dependent? They're dependent, so we can get rid of a couple of these possibilities. It's not gonna be B, it's not gonna be C, because both of these have the conclusion that are dependent. The second part is, can we use the 5% guideline? Well, that's a good question here. So let's take a look here and see if we can use the 5% guideline. So for this example, I think it's example E here. Yeah. Example. What is 5% of 15,958,866? How would you find that? How would you know if the 5% rule applied? Well, we're gonna have to do some calculations. How am I gonna calculate that? 0.05 times 15,958,866. I'm sure we're comfortably below that threshold. So 0.05 times 15,958,866. I'm getting a little bit under 800,000. So 797,943.3. So yes, our sample size is lower than that by a lot. Now, let's answer the questions here then. Are the selections independent or dependent? The selections are dependent because the selection is done without replacement. Yeah, I like that one. Yeah, that has nothing to do with the sample size. They're just dependent. When you select without replacement, they're dependent. So we'll go with that. How about the next one? The selections are dependent. Can they be treated as independent for the purposes of the calculation? So that's a good question. Can they be treated as independent even though we know it's dependent? Yes, because the sample size is less than 5% of the population. Our sample size was 1,235 adults. The population size was almost 16 million. So the answer is yes, you can. All right, looking good on that one. All right. Let's move down to example F, which I like. It's kind of fun. This is what would happen if you reduced the world's population down to a village of 100 people. And it's going to reflect the blood types of those 100 people. Now, quick question. Maybe you guys are more in tune with yourselves than my morning class. We'll see. But how many people know their blood type? Okay. All right. Better. My morning class, there was 2. All right. So if the world were a village of 100 people, roughly this many people would have type O blood. That makes you the universal donor. So now the universal receiver, I think that's AB. AB negative might be the universal receiver, or maybe AB positive. But in any case, let's take a look at some of the marginal totals. Let's write those down. That'll be helpful for us. So let's put a few in here. There, here. So there's 45 people who would have type O blood, 40 that would have type A, 10 that have type B, and just 5 that have type AB. Now across the bottom, the Rh negative, that stands for Reese's monkey, where this protein was first discovered, that's 14. Yeah, and this has to be 86, right? So we save ourselves a little brain power there. 100 and 100. Nice. Let's calculate a few probabilities. If you're selecting somebody at random here, what's the probability that they have Rh negative blood?
14
14 out of 100.
14 out of 100. So first one here, 14 out of 100. And again, let's not worry about lowest terms here for this kind of stuff. That's okay. How about this next one? What's the probability that somebody is Rh positive and has type B blood? So you want both of those things going on at the same time. Creedy? What you got for that one? They're Rh positive and B.
8.
All right, thank you. 8 out of 100. And now on an exam, I often set these up in order.
Is
Yes.
there a reason you wouldn't have the 39? Because you said O and B, correct?
Rh positive and B.
Oh, sorry.
So Rh positive and B, there's only 8 of them out of the 100 there.
Okay.
On exams, I set these things up purposely in this order because this first calculation helps you out with the second one. Let me remind you as to how and why. This goes back to our Venn diagram stuff. This stuff. When you're calculating probability of A or B, you've got to subtract off that double counting part. So this is really going to be the probability of Rh positive plus probability of B. Somebody finish this off for me. Jacqueline, what would I put here for this last one? Minus the probability of what?
Rh positive plus B blood.
Yeah, Rh positive and B. So what you're doing is just subtracting off that double counting. So like I said, a lot of times on a test, I'll put these problems one then the other in this order because you need this result to get this result. Thanks, Jacqueline. Let's fill in some probabilities here. Tisha, what's the probability that somebody has Rh positive blood?
Would it be 86 out of 100?
Yeah, 86 people out of 100. Okay, good. Let's keep going. How about the probability of type B blood?
100 over 10. Or 10 over 100. Sorry.
10 over 100. Good. Now we got to subtract off that probability of the intersection, but we've already got it. 8 over 100. So overall, we get a total of 88 over 100. Beautiful. That's your final answer there. So like I said, this one was a necessary step in calculating this one. All right. Let's go back and revisit sampling with replacement and sampling without replacement. Are we okay with this one up here though? Looking good?
Yep.
All right. All right. Ben, any questions on that one? All right, looking good. Let's calculate the probability that we draw somebody with type A blood on the first draw and the second draw. First is with replacement, second is without replacement. I'm gonna walk around and try and check in on you. If you have some questions or problems, try and get some help. If not, that's okay too. If you're watching this, try it yourself, and then fast forward until you see the end of the really cool high-tech pause button. There's my pause button. So, do the calculation for with replacement and without replacement for A1 and A2.
A1 and A2 is what?
That you draw somebody at random with type A blood on the first draw, and then you do it again on the second draw. The first calculation I want done with replacement, second one without replacement. So you put that person back, you shuffle them, so you still have 100 people. Afraid. Good. Okay. It looked like a 1. Okay. Cool. Yeah, I just chose it. We could do the same thing with any of the other ones, but I just chose this. This there was something on the door, but they had a root change. This is definitely- Okay. We lost my- just- look at the schedule. If not, you can try to effectively secretary position.
My browser froze.
Okay. Okay. All right. All right, so looking good as we went around. That's good to see. Probability of A1 and A2 with replacement. So first possibility is 40 over 100. And if you take that card out of the deck, look at it, put it back in the deck and shuffle again. So sampling with replacement, the probabilities haven't changed. Changed. So you get 40 over 100 times 40 over 100, or better yet, 40 over 100 squared. Now the difference down here is that on the first draw, there's 40 over 100, but if you're sampling without replacement, you're taking 1 out of this pool. So now there's only 39 people with type A blood out of the 99 people that are left. So those will be different. What happened here on the first event affected what the probability is on the second event. So these are dependent events. What happened on the first one changes the probability of what happens on the second one. Not so up here. Here the probabilities remain the same. What happened on the first event doesn't affect the probability of the second event. So those are independent No, that's okay. I'll keep it easy for you. Don't multiply it. The problem for me grading is that these two probabilities are gonna be really, really close. So if I were to do that second one out, the first one is gonna be 0.16. The second one is gonna be 40 times 39 divided by 100 times 99. I should have did that part in my head. So, I mean, take a look. If you round to the nearest hundredth place, they're the same. So it's hard for me to tell, did you do it the right way if you give me a decimal value? So that's why a lot of times I'll prefer fractions as opposed to decimals, because it's very easy to do the wrong thing and get the right answer. Here's my poster child for doing the wrong thing and getting the right answer. You want to put 16 over 64 in the lowest terms. Oh, I'll cancel the sixes. 1/4. All right. I mean, that's cute, but it's not really something I would give you credit for. So anyways, I do like to see some of your work. I know that a lot of these problems are going to be things you can answer without necessarily doing any work, but it's in your best interest to show me some work. That way, if there is a small mistake, I'll just take off a little bit of points. Whereas if it's wrong and there's no work, I can't give you partial credit. So it's in your best interest. Anything else on section 4.2? Feeling okay with that? All right.